We know that according to Hooke's law, stress equals K times strain, where K is a constant of proportionality. But is K really a constant value, or what does K physically signify? The stress-strain curve is divided into two regions, the elastic region and the plastic region. The slope of the elastic region of the curve gives us a quantity which is a characteristic property of the material under consideration. This quantity is called the modulus of elasticity. There are moduli of elasticity of different kinds depending on the type of stress applied and the strain produced by the given material. Consider a rod of certain material that is put under longitudinal stress, tensile or compressional. The longitudinal strain corresponding to the applied stress is noted and a curve is plotted. The slope of this curve gives the Young's modulus of that material. Young's modulus is defined as the ratio of longitudinal stress to the longitudinal strain. Since the strain is a dimensionless quantity, the unit of Young's modulus is same as that of stress, that is Newton meter raised to minus 2 or Pascal. Young's modulus is a measure of how stiff a material is. The higher the Young's modulus of a material, the more stiff it is. Titanium carbide and carbon steel has a very high Young's modulus and are hence preferred in heavy-duty machines and structural designs instead of wood, concrete or aluminium. The following diagram shows the value range of Young's modulus for different materials. We are asked to find the Young's modulus of two wires. The experimental setup requires two such wires in which one will act as a reference wire and the other as an experimental wire. The wires must be of the same material and of equal dimension. The mass placed on this span B will exert a force on the wire B. This force causes the wire to stretch, thereby causing a tensile strain. Let the initial length of the wire be L and the radius be small r. Then the mass capital M causes it to stretch by an amount delta L. Here the deforming force is the weight of the mass is added and that will be is equal to M into G. So the stress is force per area that is given by mg by pi r square. Strain is the change in length divided by the original length. Therefore, substituting the values for stress and strain, we get the value of Young's modulus as mg by pi r square into L by delta L. Consider a rectangular block of length L under shear stress and it undergoes a transverse displacement delta x or an angular displacement theta. Then the shear modulus of that material is the ratio of shear stress to shear strain. Here the shear stress is equal to F by A and the shear strain will or theta will be delta x by L. Substituting these values in the relation for shear modulus, we get G equal to FL by A delta x. The shear modulus is also called the modulus of rigidity and has the same unit as that of stress. The shear modulus of materials are generally lower than their Young's modulus. For most materials, G equals Y by 3. If shear modulus of an object is high, the object resists shear strain. That is, it tries to maintain its shape. So we can say that higher the shear modulus of a material, the more rigid the material is. As a consequence of this thought, we have to conclude that if a material has G equal to 0, the material would not be rigid at all. That is, the material has no shape at all. This means that the material is not solid at all. So conversely, for a solid, the value of G must be non-zero. Now, there exists another modulus of elasticity called the bulk modulus, which corresponds to the hydraulic stress and strain. The bulk modulus of a material is the ratio of hydraulic stress to the hydraulic strain. Consider an object of volume V. When it is immersed in a liquid, the liquid will exert pressure on the object from all sides and causes a change in the volume. The bulk modulus is given by B is equal to minus P delta V by V. The negative sign here indicates that an increase in pressure causes the volume to decrease. That is, the delta V is negative. This ensures that the bulk modulus stays positive when the system is in equilibrium. Compressibility is a physical quantity defined as the fractional change in volume per unit increase in pressure. It is a reciprocal of bulk modulus. Higher the compressibility of the material, the more it can be compressible. Higher the bulk modulus of a material, the more incompressible it is. Solids are less compressible than liquids. Gases are the most compressible compared to solids and liquids. The incompressibility of the solid is primarily due to the tight coupling between the neighboring atoms. Consider an object under tensile stress. We know that the object stretches in the longitudinal direction, but at the same time the object gets thinner. This means that it gets compressed in the lateral direction. Similarly, when an object is under compressive stress in the longitudinal direction, it gets compressed in the longitudinal direction and gets extended in the lateral direction. The key takeaway here is that when you apply stress to an object in the longitudinal direction, it also gets deformed in the lateral direction. In 1827, a French mathematician and physicist, Simon-Denis Poisson, proposed that within the elastic limit, the lateral strain in a material is directly proportional to the longitudinal strain. The constant of proportionality in that relation is termed as Poisson's ratio. It is a ratio between the lateral strain to the longitudinal strain. It's a dimensionless quantity and has no unit. The value depends on the nature of the material. The Poisson's ratio tells us how much a material will deform in the lateral direction. We know that a solid is a collection of atoms arranged in such a way that the atoms put in its position due to the action of interatomic forces. So as a solid material is under tensile stress, a work is done against the interatomic forces. This work is stored in the solid as elastic potential energy. Consider a wire of length L that is under tensile force F and it gets stretched by an amount L. The Young's modulus of the material is given as F by A into L by L. Therefore, the force can be written as F is equal to YAL by L. For a further elongation of the infinitesimal small length dl, work done dw is F times dl or YAL dl by L. Therefore, the amount of work done in increasing the length of the wire from L to L plus L is obtained from L equal to 0 to L equal to 1. That is, on integrating the equation YAL by L dl, we get the equation as YA by L into L square by 2. Multiplying and dividing the equation for work with L and then resubstituting, we'll get that the work is equal to half sigma by epsilon into epsilon square times V. Or we can say that U is equal to half times sigma epsilon V, or small u, that will be is equal to half times sigma epsilon. The different elastic moduli and Poisson's ratio of various material gives us an idea about the ability of that material. These characteristic properties can be analyzed to choose the desired material for different purposes. Think of a scenario where the characteristic property of a material is considered for a particular application. Let us summarize what we have learned.
Manorama Horizon. Learning made simple.